solving with constraints using the Lagrange multiplier. Example 1. So I've got my function f of x. So this is the function I want to find. F of x is 5x squared plus 6y squared minus xy. We assume it has a relative minimum value. But unlike the 6.3, we have it's a little more complex. Not only do I have to be a constraint critical value on my function f of x, but that critical value has to exist on the constraint equation, which means when I take x plus 2 times y, it has to be equal to, technically equal to and less than, but again, we usually write it as equal to 24. Alright, so find the relative minimum and determine the relative minimum value within that constraint. Alright, so the first thing is to set up my Lagrange function. So the first thing in the Lagrange function is to write my original exactly as is. And then it's minus the Lagrange variable times, and remember, it's times this, but you had to set that equal to 0, so it's x plus 2y minus 24, I don't know why I wrote 25, equals 0. And so it's the part where we set it equal to 0. So what you have to remember is, whenever there's a constant, you move it to the other side. Right? So in this case, we subtract. So we get x plus 2y minus 24 is my constraint equation. All right, and so there is my Lagrange formula. All right, the next step is then to find the first order derivatives. The first order derivative with respect to x, well, again, I take it piece by piece. You find the first order derivative with respect to x of the original equation. So I look here, take its derivative with respect to x. Well, that's just simply 10x. The 6y squared zeroes out. And then I get a negative 1x times y. So negative 1y or just negative y. And so there's my first piece of the partial derivative. The next part is the Lagrange multiplier comes along. It's negative lambda times the derivative of the constraint equation with respect to x. The lambda always comes along. I take the derivative of the constraint equation with respect to x. Well, there's only the 1x term. The derivative of just the x term is 1. And so I'm going to write it down because it's lambda times 1. That's what it is. And so there's the first derivative with respect to x. And now I did the same thing with respect to y. Alright, so I look at my original function, take its derivative with respect to y. So 5x squared zeroes out. I get 12y minus x. Alright, so that's the first piece. Negative lambda comes along and take the derivative. So negative lambda times the derivative of the constraint. Well, there's just the 2y. And so the derivative of the y is 2. So it's times 2. Alright, then the derivative of lambda is always negative 1. Alright, because the derivative of lambda is the negative 1 times that constraint equation. So you always get that. So the last line is always the constraint equation, negative 1. But again, the negative 1 is negligible because I can multiply it out or divide it out. Alright, so there's my 3 order derivatives. I go ahead and set them equal to 0 because, again, that's a key step, so just automatically do that. Alright, next thing is to, once I've set it equal to 0, right, that's my next step, solve the system of 3 equation. Well, in this case, it is linear. They are linear. So I can solve with a matrix because I can get a number times x plus a number times y plus a number times lambda set equal to a number, right? And so that's what it means to be linear. So the first example, it's already set up. I've got my x, y, lambda, and my constant happens to be 0. So I've got my 10x minus my 1y plus my 1 lambda equals 0, right? There's my x term, y term, lambda term. My second one, I'm almost ready to go. I just have to make sure I write my x value first, right? So it's a negative x, right? Because there's a negative in front of it. 12y plus 2 lambda also equals 0. There's no constant, so the constant in this case is 0. And the last one is always the constraint equation. The negative one is negligible because I can always get rid of it by dividing it out. And so it's really, if I divide it out, then it's just that constraint equation set equal to 0. And then move the 24 to the other side. So I get my, again, the last one is always the constraint equation, right? That's the original, and that's always the way it turns out to be. So you just kind of remember that. The last equation is always the constraint equation. Right? So x plus 2, all right? X plus 2y equals 24. Alright, so in this case, when I set up my matrix, I'm going to have, it's going to be a 3 by 4, right? There are 3 equations, and there are 4, there's 3 variables, and there's the constant, right? So I've got my x column, my y column, my lambda column, and my constant column. So the first equation is 10, negative 1, 1, 0. The second one is negative 1, 12, 2, 0. The third one is 0, 2, and there's no lambda here, so you put a 0 there, right? So it's, I don't want to put a 0 in the first one. That should be 1, 2, 0, 24. Again, the last line will always be that way. There'll be a 0 in the lambda spot. Alright, and so you type it in like that. It's a 3 by 4 into your matrix calculator. You do your RREF of that matrix, and then you get the following resulting matrix when it comes out. It should have the nice row of 1s, 0s everywhere else, and then just numbers here. And so in this case, the numbers are 6, 9, and negative 51. Remember, this column represented the x values. This is the y values, lambda. This is the constant. So x, y, lambda, constant. And so the first line is always the x value. The second line is always the y value. The last line is always the lambda. Now we find lambda. We in this class, we don't do anything other than find it. So we know lambda is negative 51. We just leave it at that. Again, we're more interested in the x and y, which is the possible optimum value within my constraint. Alright, so again, that would be the show the matrix part. So I already did the show up here, and so my optimum value is the 0.69. In this case would be a relative min, because the problem told us it assumes a relative min. And then you find it, alright? So f of 6,9, so you go back to the original function to find the actual minimum value. So you go back up here and plug your x and y in. So negative 5, or not negative 5, positive 5. So 5 times 6 squared plus 6 times 9 squared minus 5 times 6. And so our optimum value would come out 612. 612 would be the relative minimum of this particular function. Alright, so that's the first example. So that's an example where we can use a matrix. The next example is going to be the harder case. It's going to be the case where we can't use a matrix, we have to use algebra.